Hi everyone and welcome back to PrepFusion. I'm Anish and today we'll start the lecture 3 of our Magnetostatics chapter. So up until now we have learned about magnetic field intensity, magnetic force, and today we'll learn about Ampere's law. It is just similar to what? Similar to Gauss's law. In electrostat we studied Gauss law, right? It is just similar to Gauss law. Okay, the eraser is too big to reduce the size. Yeah. So before starting, obviously I gave you a few homework, so those who will do, and then we'll start with today's lecture. So these two questions only I gave you as homework, this one and this one, right? 27 and 28. This was 27 and 28 and 29. Okay, yeah. So here we derive the expression for force between two current carrying conductors. Now if I have three current carrying conductors, how will I find out the force? So what are they asking basically here? Just hold on a second, I will check with if everything is, yeah, everything is recording. So what are they asking over here? So they are asking that we have three straight parallel current carrying conductors are arranged as shown. Calculate the force experienced by the middle conductor which has a length of 25 centimeter. Okay, which has a length of 25 centimeter. Now how do I calculate these things? So basically what you need to do is, you can do it two ways. One thing is you memorize the thing that if the current are in same direction, they will both attract each other. If they're in opposite direction, they will repel, as mentioned here, right? If they're in same direction, they will attract, else repel. So either you can do or you can derive the direction as well. So both ways works, but formula you have to remember this formula. It's better that if you remember this formula, okay, it will always help you out. So we will do this question obviously. So obviously I have to find out the force experience by the middle conductor. So it will experience two forces, right? I will just copy this thing. If I observe here, it will experience two forces. One will be due to this conductor, other will be due to this. So the forces will be F21 and F23. What will be the direction here? So obviously both of them are in opposite directions, so both will repel. So this will also get repelled in this direction. F22 to F21 will be in this direction, and F31, right, it will also repel it. It will be in this direction. So they will be opposite to each other. Don't worry, I will derive as well what is the direction, but just I am explaining with the shortcut method. So obviously I will directly write my F net on 2 will be, I will assume a reference. Okay, I will assume that this direction to be my reference. Why? Because this length is smaller, so this force will be actually bigger. So I will just assume it to be my reference to get the positive answer. That's it. There is no other reason. So it will be F21. Just I will write the scalar formats F21 minus F31. So what is F21 basically? So F21, right? F21 is simply mu I I1 I2. So what is the current between these two? 30 into 10. So it will be, I will just write this directly now. Mu, and this is in the like nothing is mentioned, so I will assume it to be in the vacuum, into I1 I2 into the length, okay, divided by the 2 pi d, right? Into the length is how much? Length they have told me it is of 25 centimeters. So 25 into 10 raised to power minus 2 divided by 2 pi. Distance is 3 centimeters. So anyway, centimeter gets cancelled. 3 into 10 raised to power minus 2. Minus, same thing only. This will be mu naught into 10 into 20, because this current is 20. 20 into length is 25 only, 10 raised to power minus 2 divided by 2 pi. The distance this time has increased, it is 5. 10 into 2 raised to power minus 2. So this will become 1. This will be, if I take mu naught and all those things common, right? Mu naught and by 2 pi if I take common, this will be, and 25 also I can take common, right? 25, this will be 100 also I can take common. 3 by 3 minus 2 by 5. So what is mu naught? It is 4 pi into 10 to the power minus 7. So it will be 2 times 10 raised to the power minus 7 into 25 into 10 square into 1 minus 0.4. So it will be 0.6 basically. Okay, so it will be 1. This is 50 times this will be 50. 10 will go. Okay, 50 times 0.6 is 50 times 0.6, right? Or 5 times 0.6 is 3. So 10 goes here, 30 goes here, minus 4 Newton. Okay, this will be the net force on 2. Okay, so if I observe, in what direction it will be? It will be on this direction. This was my initial reference direction, right? And it is coming positive, so obviously it will be on the right hand side. It will be on the right hand side, right? Right. So option A will be correct, because here it is telling me the magnitude is 3 into 10 raised to minus 4 and right. All the options are right only. So the direction will be on the right. Okay. So like how I would have done if I would have forgotten this concept that okay, opposite currents repel each other. So how you can do is the same thing only. Just you assume that this I1 is generating some magnetic field. It is going inwards, right? It is going inwards. Okay. Now what will do? It is going into the screen, right? Going into the screen. As it is going into the screen, again I will have two vectors. What is the DL direction? Downwards. So DL direction is downwards, and it this is going into the screen. So again I will do this IDL cross B. So it is on the right hand side. IDL cross B is on the right hand side for this I1 element. For this I3, what will happen? I3 is upwards, so magnetic field will come out, right? If I just curl my fingers, magnetic field is coming towards me, so it will be point. So I will just put this in front of me, right? This pointer in front of me, and ideally second bottom. Again, ideally side bottom. So I'll just if I somehow place my fingers like this bottom and then curl my fingers, the direction of my thumb is on the left hand side. It's on the left. So this the force on force due to I1 is on the right hand side. Force due to I2 is on the left hand side. Obviously I1 will have more force because this distance is smaller. Everything else is same almost. Current is also less here, right? So force inverse here will be less. So obviously the final direction will be on the right hand side. Magnitudes, I have told you how you to find out. Formula you need to remember. That's it. Formula you need to remember. Okay. So that's how we solve this question. This was a pretty simple question. Let's now solve the second question. This question I gave as homework, right? So here we have a magnetic field that has a magnitude of 1.5 millitesla. So its magnitude is 1.5 millitesla. And an electric field has a magnitude of 4 into 10 raised to power 3 Newton Coulomb. Okay, both fields are oriented in same direction. Okay, so I will just assume any direction, any random direction. Okay, I can assume, let's assume for now, let's say ax cap direction. Assume any direction, right? Ax cap direction. Okay, doesn't matter. A positive charge of 1.8 Coulomb moves with a speed of 2 into 10 raised to power 6 meter per second in a direction perpendicular to both the fields. So I have a positive charge and the velocity of the charge is 2 into 10 raised to power 6 meter per second in a direction perpendicular to both. So I will assume it as ay cap direction. Ay cap is in the direction perpendicular to both the fields. Okay, and it is a positive charge of 1.8 Coulomb. So the value of the charge is 1.8 coulombs. Now what we have to find out? We have to find out find the magnitude of the net force acting on the charge. So what is that force? It is a Lorentz force because both magnetic and electric fields are present and nothing is mentioned about the behavior of the fields. So I will assume it to be uniform fields. So my force will be basically Q times E plus Q V cross B. Correct. So I have just assumed that as they want just a magnitude, so I will just compute the magnitude only. So basically it will be Q is 1. Q I can take common. E is 4 into 10 raised to power 3 nano coulomb plus, and I have to obviously write down the direction. Direction is in the direction of the electric field, that is Ax cap, plus V cross B. V is in the AY cap direction and B is in the AX cap direction. So AY cross AX will be simply minus AZ, right? So I'll just write this thing down. It is 2.2 into 10 raised to power 6 into B is the constant. What is the constant? 1.5 into 10 raised to power minus 3 into AY, V cross B, right? AY cross B is AX. So this will come out to be, Q is how much? Q is 1.8 coulombs. So it will be 1.8. So this will come out to be 4 into 10 cube AX minus 3 into 10 raised to power whole cube AZ, right? Because it is minus AZ. So now I have to just find the magnitude. So I can simply find the magnitude. So what will be the magnitude basically? Just hold on. Is there some mistake over here? I will check. Okay, this was millitesla. Millitesla is fine. Positive charge of 1.8 coulombs. Actually, I think I missed a micro over here. This should have been a micro charge, right? That's why what am I missing? Because the force value would be coming very huge. That is not possible. This is a micro coulomb charge. Okay, so this actually is a micro coulomb charge. Minus 6 coulombs. So overall here, right, 10 raised to power minus 6 also will get multiplied. Okay, so now I just need to find out the magnitude because they have asked the magnitude of the force. So what will be the magnitude of the force? It will be simply 1.8 will be outside, 10 raised to power minus 3 will be outside, whole under root 4 square plus 3 square, and this value won't change even if you change the direction, right? According to the question, if you choose, this value won't change. So this will be 5 into 9. So this will be 9 into 10 raised to power minus 3 newtons. This will be the answer, the magnitude of the force that will act on that particular charged particle. Okay, I hope you get the point. Very simple. Just you have to directly calculate the Lorentz force. It is just the summation of both the forces due to magnetic field and the electric field. Okay. So now we start with today's lecture, that is Ampere's law. So what is Ampere's law? Ampere's law is used to calculate the magnetic field. Ampere's law is used to calculate the magnetic field in symmetrical current distributions. Wherever there is symmetry, we will use Ampere's law. So just same as Gaussian law, right? We will choose Ampere's law is to Biot-Savart law, but Gauss's law is to Coulomb's law in electric field. So we can skip the Coulomb's law and derive using the help of Gauss's law. But obviously there needs to be symmetrical cases here. If the symmetry is present, then only Gauss law will help me, else it is very tedious for me to derive the expression for any electric field with the help of Gauss law. I have to go solve with the basics. So Ampere's law is something same only, just you have to, again, if the circuit is symmetrical, then you will be able to use Ampere's law, else if it is not symmetrical, you have to solve using the Biot-Savart law. Now in Ampere's law there is a term named Ampere circuit. Okay, so it is a closed loop basically. It is Amperean circuit is similar to the concept of Gaussian surface. If you remember, I had a Gaussian surface, right? It is similar concept like that, but few differences are there obviously. So like just I am giving you I'm just trying to tell you the past as well, so that you can relate with the previous things whatever you have studied. So an Amperean circuit is a closed loop along which Ampere's law is applied. So it's not a surface, it's a closed loop. It is a closed loop. This is the first point, this is the first difference. Now how do I assign the direction of closed loop? Because a loop can be in this direction or in this anti-clockwise. How do I assign the direction? Assign a direction along the loop using the arrows. Okay, I will assign a direction of the loop using the arrows, but how will I choose the direction? That also I will explain. Use the right hand thumb rule to identify the positive side of the loop when the fingers follow the direction of the arrow and the thumb points to the positive side. So first of all, this current direction, how do I choose? I will tell you later on. But first let's assume this is the direction of the current and this is the loop that I have chosen. So can you tell me what is the positive side of the loop and what is the negative side of the loop? Again, you will use the right hand thumb rule. So if I use the right hand thumb rule, I will just curl my fingers and I'm pointing upwards. So pointing upwards meaning it is the positive side. So AZ cap is the positive side. Again, for this case, if I am pointing like this, it is downwards, right? So the downward is the positive now. Here upwards, for this loop, the up is positive. For this loop, the down is positive. Okay, I hope we get the point. Which one is positive? Okay, so that is the important point that I want to tell. Just with the help of right hand rule, just curl your fingers along the loop and your thumb will tell the positive direction of the particular closed loop. So what is the statement of Ampere's law? Before understanding the statement, let's first understand this line integral of a magnetic field. What is line integral of a magnetic field? The line integral of magnetic field B around the Ampere loop is calculated with B dot dl. Basically, if some magnetic field is crossing through this, right? And if I just take the line integral throughout this closed integral, that will be the line integral of a magnetic field around the Ampere loop. Now this is, just remember, this Amperean circuit is a fictitious circuit, just like Gaussian surface. Gaussian surface was a fictitious surface, right? So this Amperean circuit is also a fictitious, like it doesn't exist in real life. We just assume that a closed loop is there, right? So this is a fictitious loop. It is not really present over there. We're just assuming it. So this is the fictitious loop that we're assuming, and the flux that will, the magnetic field, the line integration of the magnetic field that will pass through this fictitious surface, right? Due to this fictitious surface will be basically B dot dl. Okay, line integral will be simply B dot dl, the amount of magnetic field intensity. Okay. Now Ampere's statement says that the line integral of the resultant magnetic field intensity around any closed path is equal to the net current that passes through the area enclosed by that path. So the magnetic field intensity around this closed path, right, closed path, will be equals to what? The line integration of the magnetic field intensity around this closed path will be equals to the net current that crosses through the surface area of this path, okay, of this closed loop, the net current that crosses through the surface area formed by the closed loop. Okay, so that is a statement of Ampere's law. So the Ampere's law, they stated in terms of magnetic field intensity, but I can change this in terms of magnetic field, magnetic flux density as well. Like magnetic field intensity is equals to what? H equals to B by mu naught. That's it. That's the difference. Just a constant term. So I can take the mu naught on the right hand side. So the modified Ampere's law will come out to be this. It is integration, closed line integration of B dot dl is equals to mu by I net. What is I net? How to find out I net? Don't worry, I will explain all those things. Just try to grasp each thing one by one. Okay. So what I'll do, the closed line integration of B dot dl. So let's say magnetic field is like in this particular region, magnetic field is in this direction, and what is my dl vector? Dl vector is in this direction. Okay, so what I'll do, I'll just do simple B dot dl, and if I keep on adding this small B dot dl, right, and the resultant will be equals to what? Throughout of a closed loop, the resultant will be the net current that crosses through this whole loop, right? What will be the net current that will cross through this whole loop? Okay, that will be simply the magnetic field around this loop. Okay, this is not the current actually. I should not write current. There is no current here. Okay, I have just assigned a direction to this loop. That's it. I have just assigned a direction. There is no current here actually. This loop doesn't have any current. Okay, I have just assigned a direction to this loop. Later on we will understand about current is flowing through the surface of this loop. Okay, current is flowing through the surface of this loop. So that is the case. So now what I can say is that now how do you find out few things. First thing is how we will find out what is the net current that will come out of this particular closed loop. So for that I have taken few examples. Okay, this is not I. Okay, this is just a direction. So the orientation. So I have given you the orientation. Now out of this orientation, can you tell me what is the positive direction and what is the negative direction? So like if I just see this as in the screen, okay, in the XY plane, okay, if I just rotate my fingers along, curl my fingers along the loop, I am saying it is going inside the screen. So for the case 1, inside will be positive. So here I was explaining it top or bottom, or you can understand this is on the screen itself, on the plane itself. So for this case, if I just curl my finger, it is coming towards me. The arrow is coming towards me. So it's coming towards me. This time my outside, the arrow coming towards me will be positive, and in this case it is in the clockwise direction. It is just in the clockwise direction. So if I just rotate in this direction, it is going away from me, going into the screen. So if it is going into the screen, the positive direction for this case will be simply a cross. Okay, the positive direction will be simply a cross, and for this it will be simply a dot. Correct. So here also pause the video, try it out by yourself, that what is the net current that is passing through this closed loops. What is the net current? Okay, so just try to identify the orientation of the loop, and from there identify what is the positive and what is the negative, and then find out the answer. Okay, so I will solve the first one. So the first one, I observe that there is a 4 amperes as well outside. So in the first case, if I just copy this, will this outside current, right, contribute to my I enclosed? Will this outside current contribute to my I enclosed? Let's just read the definition of I enclosed. I net. I enclosed or I net. It is a total current crossing the area bounded by the curve. Bounded by this curve, net current that crosses the area. So will this current cross? No, right? This current will not cross any area bounded by this curve. So obviously this current is simply useless. So any current outside the bounded curve, okay, will be useless. I will ignore that simply. Now, if I curl my fingers along the direction of the orientation inside, it is pointing going inside. So obviously, according to the orientation of the Ampere loop, inside, okay, inside is the positive one. Okay, this is the positive. So I will write that. So total I enclosed or I net. Okay, they call it some different names as well. I enclosed, I net. This will be equals to what? Inside will be positive. Okay, okay, so yeah, inside is positive. This will be not dot, this will be cross. Inside will be positive. So if inside is positive, 1 is positive, 3 is positive. 1 plus 3. What is negative? 2 will be negative, because 2 is coming towards me and 2 is the opposite. So 2 will be simply negative. So I will subtract a 2. So this will become 2 amperes. Okay, this will be I net according to direction. Okay, now for the second case. For the second case again, I will rotate my fingers and find out the direction of the positive direction of the loop. So again, it is in the anti-clockwise direction, so it is pointing towards me, coming towards me. If you just rotate your fingers, it is coming towards me. So if it is coming towards me, then obviously this time dot will be the positive direction. Okay, and this 4 ampere will again be useless, because this is not crossing. Cross section of the Ampere loop is this, right? This is the bounded area that the curve is bounding. Okay, basically. So this is not this 4 ampere is not bounded by this area. So obviously I will ignore this 4 amperes. I will only write this. So again, 1 ampere is positive and 2 and 3 are negative. So this time 1 I net will be 1 minus 2 minus 3. So this will become minus 1 minus 4. Minus I net will be simply minus 4 amperes. Okay, this will be my I net. What about the third option? Third case. So in the third case is a bit interesting. If I just copy this configuration, here I have 2 wires. Now what is the orientation? This is not I, actually. This is not I. What is the orientation? The orientation is like this. I will just again curl my fingers. Top. It is going top. So top will be positive and down will be negative. So I1 is in the top direction. That the area enclosed by this is this, right? So I1 is actually inside this area. So I1, I net will be I1, and I2 is in the opposite direction, going downwards. Up is the positive, down is the negative. Minus I2. Okay, so this will be my I net, and because these both current are crossing. If this I2 was, let's say, here, obviously I wouldn't have written I2, because it is not crossing the bounded area by the Ampere loop. Okay, so this is how we find I enclosed. I hope you understand how we find I enclosed, just same as charge enclosed. Okay, there it was charge inside, here it is current within the bounded area. So again the same statement, I net is the net current passing through the Ampere loop in the assigned positive direction. So as this negative represents what? My actual direction of the Ampere loop is coming out of the screen, but it is saying I net will be going into the screen. So this negative has this significance. That is the significance of this negative, right? So now B is the resultant magnetic field due to all nearby current distributions. So with the help of this, what we will do, we will find out I net. Okay, then as or due to symmetry, B will be some uniform constant thing. So I will take it out of the integration, and with the help of that, I will be able to simply derive the expression for magnetic field intensity due to different distributions. That is my aim. So finding out I net is very simple. How easy it is to find out the I net? Very easy, right? Then just simply this this B will be constant, so this can come outside of the integration. Then I can simply manipulate equations, and I will get my equation for magnetic field intensity due to different current distributions. So we'll solve it for one of the cases. One case is magnetic field due to infinitely long thin wire. Now we cannot apply this Amperian loop for a finite thin wire, because you have to use basics. To solve that, you have to use basics, because that case is not symmetrical. There cos alpha plus cos beta comes. But as this due to infinitely thin wire, the case is symmetrical, we can simply solve it using the Ampere's loop. So let's come to the how to apply this Ampere's law, right? Let's come to the application. Please listen to me carefully here. So there is a like straight wire that is carrying a current I, and it is infinite. Can you tell me the direction of this magnetic field at this point P? Okay, I will just this is top. Okay, this is the top view. At this particular point P, what will be the direction? Direction, what I can say, this is a side. I'm just talking about this view right now. Don't ignore this one for now. Direction will be, if I just place my thumb along the current and just curl my fingers, it is going inwards. Okay, and what is it? It is simply like a circular magnetic field, because magnetic field always exists in a loop, and we know it will be just like a whole circle. At this distance r, the magnetic field will just be like a whole circle. That is point 1. That is the behavior of magnetic field. Obviously, to derive the expression for magnetic field, few things you have to know previously, same as Gauss law. Now this is the side view of this infinitely long wire. If I see it from the top, this is the wire, right? This is the wire. Now if I see it from the top, I just see a small dot that is coming towards me. So current is coming towards me. So that's why there is a simple dot. It's the significance is the current is coming towards me, and this is the point P at a distance r. This is the top view, and this is the side view. Okay, so now the magnetic field will be how? From the top view, magnetic field will be something like this, right? Magnetic field will just be like a circle of radius r at this particular point, right? So what type of Amperian loop shall I choose? Same as Gauss law. What type of surface did I choose there? Sometimes I choose sphere, sometimes I choose cylinder. Okay, according to my own convenience I choose. So here, what convenience I shall see? Simply I shall see the angle between the dl and the magnetic field should be always, I should always try to keep it 0. Okay, I should always try to keep it 0. There as well, I always try to keep the angle between the area vector and the electric field to be 0. Here also I will try that. So I know that magnetic field will be something circular. So won't it be best to choose a circular loop? If I have chosen a circular loop, then the angle between the magnetic field and the dl vector will always be 0. It will, because the loop itself is telling me that it is circle, and the magnetic field also is also circle. So the angle between the dl vector and the b vector will always be 0. So things will become very simple. So what I will choose? I will choose a circular Ampere loop. So as magnetic field is circular, we choose a circular Amperian loop. Okay, we choose a circular Amperian loop. Now if you choose a circular Amperian loop, what advantage it gives me? Simple advantage it gives me is that I'll just here, if I just show you in the bottom, right? If I just take this, copy this thing, simple advantage what it will give me, is that simply the angle between, this is still not the center, yeah, this is not the center. So the angle between the dl vector here and the b, right, dl vector and the b will always be 0. So bl dot d dot dl, right, will get converted into b, and I know b will be uniform, it is constant. That much information you need to know. So it is cos of 0, so it becomes simply b dl. Okay, so this vector integration gets converted into simple scalar integration. That is the main purpose of me. And what is the I net? Now the main thing comes in what direction you should choose your Ampere loop. You should choose what is the orientation of the Ampere loop that you should choose. You should choose the Ampere loop along the direction of the magnetic field. Okay, what is the in what direction magnetic field will be? I know magnetic field will be something like this, right? Something like this, right? According to the current, from the top view, if I see, it is in the anti-clockwise direction, right? Anti-clockwise direction. So that is the direction I will choose. So choose, second point, choose orientation of Amperian loop just hold on, why did it go on this one, right? I was just thinking something else here. Yeah, okay, so brightness is sometimes going up. Amperian loop, just hold on. Along b vector, like then only the angle will be 0, right? Then only this dl vector and b vector angle will be 0. If I choose the orientation like this, it will be, angle will be 180. This will just an extra negative sign will come. So I have to choose the orientation of Ampere loop along the b vector. So orientation will be in this direction, anti-clockwise. Now I know what is positive for the current and what is negative for the current. Okay, so now you get the idea. Now what you can do is simply derive the expression. So this thing, right, this thing gets converted into this. What is the I net? Now if I curl my fingers along the Ampere loop, I can see that coming in towards me is the positive direction. So the current is actually coming towards me only, so it is positive. So I will write integration of b dl mu I, as it is coming towards me, it will be positive, plus mu I and b will be b is constant. So I can take b outside. I know b is uniform, so b I can take outside, and this will be integration of dl. Dl from what? Throughout this whole Amperian loop. I will just follow. This is the closed integration, right? Closed integration of this curve, Ampere curve. So L will go from 0 to 2 pi r. Correct? 0 to 2 pi r. That is the whole integration of dl, right? 0 to 2 pi r. R is the distance here. That is equals to mu I. So your b comes out to be mu I by 2 pi r. Now isn't this what you derived in the lecture 1 of electromagnetism? The same thing, right? So with Ampere's law it is so simpler, but obviously we cannot compute for unsymmetrical cases. It is very difficult for us to compute for unsymmetrical cases. Okay, so like what are a few tips for choosing the effective Amperian loop? The magnetic field, obviously we will use Ampere's law only there when the magnetic field is constant or 0 at every point of the loop. Here, right, at every point of the loop the distance is always mu naught by r, mu naught by distance is always r, and the magnitude of the magnetic field will always be constant. Okay, that's why we choose the Ampere loop like a circle. At each point of the loop, the magnetic field lines should be either parallel or perpendicular to the loop. Why it should be parallel? Parallel means in the same direction, then cos 0. Perpendicular meaning 90 degree. That means the integration will be simply 0. So either it will be 0 or it will be simply B dot dl. Nothing else, right? If it is something else, then the integration, this computation will be very, very difficult. And we want to make our life simpler, not difficult. So we will ignore the Ampere's law. We will use something else. Use Ampere's law only in these two cases, as explained. Now let's come to the derivation of a magnetic field due to infinitely long hollow cylindrical wire. Okay, this is a thin hollow cylindrical wire. So this I haven't derived using Biot-Savart law because I wanted to derive using the Ampere's law, because with Ampere's law things will become very, very easy. Again, if I have a thin infinitely long, this is infinitely long, right? That is the thing that you need to take care. Infinitely long hollow cylinder, the magnetic field inside will be what? If I just, what type of Amperian loop I will take? I will take again Amperian loop as a circle, because magnetic field will be again circular in nature. So I will take a circular Amperian loop. So if I have taken a circular Amperian loop, right? So I will just reduce the size and I will just duplicate this. So if I just take a circular Amperian loop here, okay, okay, just hold on. Here, if it is a circular Amperian loop and orientation, I don't know yet about the magnetic field. Okay, I can take anything. But what is the I enclosed? It is a hollow cylinder, right? I current is only on the surface. So as it is hollow, current only at surface. So obviously for this case, right, my I net will be simply 0. Hence my electric field will also be simply not electric field, sorry, magnetic field will also be simply 0. B inside will be simply 0 because there is no current inside. As there is no current inside, the magnetic field also will be simply 0. Now if my R is greater than capital R, that is I am lying outside. If I am lying outside, the derivation will be same. Okay, again I will choose a Amperian loop. Okay, choose Amperian loop like this, and if I choose an Amperian loop that is at a distance r, small r, what am I observing? Again, what is the direction of the magnetic field? It is something like this, right? If the current is flowing in this direction, the direction of the magnetic field will be in this direction. So I will just assume that same direction, right? I will assume the same direction as the direction of the magnetic field. So again, what it will become? B dot dl integration, closed line integration should be equals to mu times I net. So what does it become? It becomes B dl, vector goes away, becomes cos of 0 degrees closed line integration equals to mu, what is I net? Now this is the orientation of my surface, and through this whole cross section how much current is flowing? This I current is coming towards me, and the orientation is same as the current, positive direction. So current is in the same direction according to my convention. So I will choose here plus I. Okay, the same expression I get back. Again I will integrate with dl, what? Dl from 0 to 2 pi r. So it will be again like your magnetic field will again come out to be B will come out to be mu by 2 pi r. Okay, so direction, obviously few things you need to know, then only you will be able to answer it. Okay, so I hope you get the point how you can like write use the Ampere's law. Can you do the same? Like this is the expression for magnetic field due to a infinitely long hollow cylindrical wire. Okay, can you just draw the graph? Inside, magnetic field will simply be 0. Okay, for rho less than r, magnetic field will be simply 0. It will not be present. And just outside, just at this point, magnetic field will be very high, and then it will start decreasing, right? So it will be something like this. It will be something, I'll just draw this. It will not be a continuous line, something like this, right? this is rho equals to capital R. So at the periphery of the area, the magnetic field will be huge, and before it, magnetic field will be simply 0 inside, and outside it will be simply follow like a long cylindrical wire. Okay, mu naught I by rho is given just to write in the cylindrical coordinates. That's it. And this a phi is just to show the direction of the magnetic field. That's it, right? Now, with the help of this particular thing, can you do the same for an infinitely long cylindrical wire? Pause the video, try to derive it by yourself, the expression for magnetic field for a long cylindrical wire, both inside and outside. Okay, this is for a thick cylindrical wire. So it is thick, as it has like the current is now distributed throughout the volume, both inside and outside. So first do it for two cases. First for R less than capital R, and next case will be this case one. Next case will be for R greater than capital R. Okay, outside and inside. Try to solve it by yourself, and then I will solve it. So let us start with the derivation. So in the case for R less than capital R, right, things will be a bit different. What will be different? Here I will just copy this particular thing, okay, and just at least you could have told me that what type of Amperian loop you have chosen. What type of Amperian loop I must choose here? I must choose a circular Amperian loop. Why is that the case? Because if I observe, as this current is distributed everywhere throughout this volume, right? If I choose a circular Amperian loop, what will happen? The current inside is in the same direction, whatever this direction is. If I put my thumb along the direction of the current, the magnetic field will be something circular. So that is the reason to choose a circular Amperian loop. So I will choose a circular Amperian loop here. I'll just delete this thing, okay, and I will choose a circular Amperian loop. So circular Amperian loop is done, and the radius of this Amperian loop will be simply smaller. Okay, and obviously smaller is less than capital R. Now, how do I use the Ampere's law? So what does my Ampere's law say? So here, whatever the magnetic field, so I have to assign a direction, right? What will be the direction? Direction should be along the direction of my assumed magnetic field. So the current direction is this. So if I just curl my fingers, like if I just put the finger along the current, so my fingers are rotating like this, right? Something like anti-clockwise. So I will choose the orientation of the Amperian loop as anti-clockwise. Okay, fine. So that is the orientation, because that is the expected current, like magnetic field direction. And the magnetic field will be along this direction only, right? So if I just use the Ampere's law is B dot dl equals to mu into I net. So it will just be replaced with B dl cos of 0, because the angle between the dl vector and the magnetic field are same. They are just almost one over the other, right? Equals to mu into I net. Now what is the I net? What is the positive direction? Curl my fingers along the Amperian loop. It is coming towards me, coming outwards on the left, right? So I net is how much current is in this particular surface. Okay, let's assume that current to be I dash. Inside this, how much current is crossing this cross section? Because what was the definition? Definition was the net current that was crossing the cross section or the area formed by the closed loop. Okay, so this is the area, right? So here I will assume that the current is uniformly distributed. Now if the current is uniformly distributed, can you find out the current per unit area? What will the current per unit area? Current per unit area will be I, the total current, divided by pi capital R square. I hope you are understanding this, because in this whole cross section the current I is uniformly distributed, so it will be I by pi R square. Now, but I want to find out the current in this small area. Simply I need to multiply this current per unit area into the required area. What is the required area? It is pi small r square. So I will multiply pi small r square and I will get my I dash, the current that will cross through this enclosed Amperian loop. So I will just replace my I dash, I will put this below. I will just replace my I dash to this in this equation and I will get my answer. So this will be B. Again, how will I integrate my DL? DL again, right? Will integrate a whole 2 pi r from 0 to 2 pi smaller. So DL 0 to 2 pi smaller equals to I into pi smaller whole square divided by pi capital R square. So this will become B equals to this will be 2 pi r, pi will get cancelled and r also will get cancelled. I will be left. Okay, here already a pi has been cancelled, right? So this 2 pi r will directly come here. Yeah, and 1 r will get cancelled. Okay, fine. So B will be equals to I r divided by 2 pi capital R square. So this will be the value of your magnetic field if the radius is lying inside. Okay, if the radius is lying inside, then this will be the value of magnetic field. Obviously I forgot the mu here, forgot to write the mu. So mu is obviously in front. And direction you can identify easily. So yeah, the expression is a bit different than what we knew. And what will be the outside magnetic field? If I observe at the outside, right? If I observe at the outside, what is the I enclosed? I enclosed is simply I, right? Whole of the current will flow through that closed Amperian loop. So the expression will be same. So this is the B inside. And outside I won't derive. Outside it will be same, right? V outside it will be same as the previous case for a thin cylinder. Just it will be mu not I by like I am just deriving it for a general case. I will not write mu not, mu I divided by 2 pi distance smaller. Okay, so just have a bit of care about the formulas, right? Inside it will be something else, outside it will be something else. Just be careful. So inside it is linearly increasing. Why is it linearly increasing? As the current is increasing, right? Current is increasing. The current enclosed by the cross section is increasing. But outside it is decreasing in inverse fashion. Why? Because obviously the distance from this point is increasing, but the current is same. The current is same, but the Amperian loop radius is increasing. That's the reason. So here I've written basically this arrow cap can be in AB cap direction because this can be in any random direction, right? Depends actually. So if it is in cylindrical coordinate system and if I just place the current according to this, then this will be in the arrow cap direction. Okay. So basically here what they are telling is if my radius of the cylinder is inside, right? If I'm inside, obviously the formula will be mu naught I rho by 2 pi r square. Just instead of r I have replaced with rho. And if I'm outside, it will be same as the previous case. So can you plot the graph for me? So if I observe in the inside, right, it is actually linear graph. This r square is a constant term, right? This will not change. So this is varying according to rho. So obviously what is happening, from 0 I'm increasing slightly linearly. Then again at this point when my small r equals to capital R, it starts to decrease inversely, right? Okay, so this will be decreasing like this. Okay, so here my magnetic field is inversely proportional to R, and here my magnetic field is directly proportional to R. So these two are the cases. I hope you get the point. R, or you can say rho, because we have chosen rho. I will just use the rho. So let's do a few questions according to this concept. So we have a question here. So consider a coaxial cable consisting of an inner wire with radius A. So it is a coaxial cable with inner wire with radius A. Okay, fine. And radius is A. Inner wire radius is A. Okay. And what is the what are they telling? Small a. Okay, it is small a, and surrounded by an outer shell with inner and outer radius B and C. Okay, inner and outer wire radius B and C. Okay, respectively. The inner wire carries an electric current I, and the outer shell carries an equal current in the opposite direction. This carries an equal current in the opposite direction, and this carries an equal current in the same direction. Okay, fine. Determine the magnetic field at points A, B, C, D. So this is the point A, this is the point B, this is the point C, this is the point D. So we'll just copy this figure. Actually, the current direction they haven't shown. Just copy this and properly note down the current direction. So they're telling me that inner wire radius with radius A. So this right, this particular thing has a radius of A, and the outer, surrounded by an outer shell with an inner and outer radius of B and C. So this is the cell, right? This is a cell. So its inner radius is B and its outer radius is C. Okay, got it. Now the inner wire carries an electric current I, and the outer shell carries an equal current in the opposite direction. So if I assume the inner wire to carry a current I towards me, okay, if it is coming towards me, then the outer wire will carry a current in the opposite direction. So it will be simply cross. Okay, so I hope, like, this is just a top view I'm giving you. So just to get a brief overview, this is I, this is also I. Okay, just whatever the information that the question has given me, I have drawn it pictorially here. Now determine the magnetic field at points A, B, C, D. So what is the magnetic field at point A? A is at center. Okay, A is at center. So will there be any magnetic field at center? Will there be any magnetic field at center? Can you tell me? There will not be any magnetic field because no current can pass through, right? Center means zero radius. Okay, a point, just a point here, and no magnetic field is crossing through this point. So obviously at the center, magnetic field at A will simply be 0. So this one was simple. Let's solve for the second case. Second case, we have to find out the magnetic field at point B. So B, I am observing it is at a R1 distance from here, but it is still inside the first wire, right? So it is inside the first wire. So the magnetic field will be produced due to what? Only due to this wire. It will not be produced due to this, because here no current will this outside shell, right, spherical shell, no current of this spherical shell will actually cross through this particular area. So I can say magnetic field at B will be what? Magnetic field at B will simply be this thing, right? I have just derived the formula. I will just directly use it. It is mu into I. So I am assuming I to be this direction to be positive, right? I am assuming coming towards me is positive. So I will take the Ampere loop as anti-clockwise. So mu I into R, mu IR divided by 2 pi R square. Okay. So this will be the magnetic field, and here R is what? R is R1, because they have given me the distance from the center, it is R1. So this will be simply R1. This will be the magnetic field for the second point, okay, at point B. Now what about the third point? Third point is where? Third point is this is a small radius. Third point is here, just at the edge, just at the surface of this particular configuration, coaxial cable. So can you tell me what will be the magnetic field at this point? The magnetic field at this point actually will be due to this and due to this also, because this is all of the current will flow, because if I take an Amperian loop of radius small c, all of the current will flow, right? All the current will flow. Here I forgot to mention this radius R is, capital R is what? This radius, right? Small a. So it will be simply a square. Okay. So I hope we got the point. Now what will be the magnetic field here? Magnetic field at C. So magnetic field at C obviously will be due to two things. Due to this one and due to this one as well. Am I correct? So what will happen here is that, what is the I enclosed at this point? What is the I enclosed? So at this point, if I observe, coaxial cable inner and outer cell carry equal and opposite. Inner wire carries a current of I and the outer cell carries an equal current in the opposite direction. Okay. So what will be the I enclosed if I just choose this particular section, right? What will be the I enclosed here? So if I observe, the I enclosed will actually be both these currents. Okay, so it will be due to, so here at B at C, right? Now I will use this so simple formula because this is not standard anymore. So I have to find out the I enclosed. So here if I choose an Amperian loop, which is a circular Amperian loop, right, of radius C. So it's of radius C, then this current is there that I have assumed it to be incoming, which is of magnitude I, and another current of equal magnitude but in opposite direction is also there, that is coming out of this Amperian loop, right? So cross is there, which is also I. Okay, so overall what I can comment on is that overall I enclosed at this point C, right? Okay, I think somewhere I made a mistake, because this point C actually should not be here, it should be somewhere here. That is a mistake that I have made, I think, because the result for this would be something else. Yeah, okay, yeah, that is a mistake that I am making. So here, right, this is not the C, actually made a mistake. So I was thinking, but where am I making the mistake? The C actually is present over here, okay, at a distance C. That is the mistake that I'm making. Okay, yeah, I was thinking, why am I making the mistake? So this C is at a distance C from this particular point. So like what I'm telling is here, right, in this particular section the I enclosed is what, only it is covering this small cable, this outside thing it is not covering, right? So this is somewhere outside, this I is actually lying outside the C point. This is a Amperian loop with a radius capital C. So now can you tell me what will the magnetic field due to this? Because this I is constant, right? This I is constant, it is not varying. Okay, just hold on. This I is constant, this is not varying basically. So obviously I can directly say I enclosed will be only small I. Okay, and my magnetic field will be what? B. Okay, what happened? B will be simply mu naught. It's just simply due to a wire. R smaller greater than R. So this is the second case, right? Second case basically. So it will be simply mu I by 2 pi capital C. So this will be the magnetic field, okay, due to the third case at the C point. Now what about the fourth case? Fourth case is again interesting. So in the fourth case, what am I observing is that I am at a distance R2 from the center, and what is the net current through this Amperian loop? I will again choose a circular Amperian loop. So if I choose a circular Amperian loop, this time this I current, right? This time this I cross I current is not lying outside, it will lie inside the surface. So, Amperian loop basically. So I have a I current that is coming towards me, and I have a cross I current that is going out towards the screen. So I have two currents, and whatever direction I have chosen according to this convention. So it will be in the anti-clockwise. It doesn't matter because my I enclosed, okay, or the I that goes through the Amperian loop surface is simply 0. So if it is 0, my magnetic field will also be simply 0. Correct, because the angle between magnetic field and dl is 0 only, so I can safely say here magnetic field will be simply 0. Or you can write it otherwise. How you can write? You can say that the magnetic field due to the smaller cable is mu I by 2 pi r2, and magnetic field due to the larger cable is again mu I by 2 pi r2 only, because same, they are flowing the same current but in opposite direction. So obviously this 2 will cancel and the result will be 0. Okay, so these were a few basic questions that you should do. Now let's come to another format of Ampere's law, that is a differential point format. So I have told you about a term known as volume current density. I have talked about that term, right? So here we will actually derive the expression for volume current density as a function of magnetic field intensity. So we'll do the same. So what I know is this is a J, and if I integrate this with respect to ds, if I integrate this with respect to ds, I will be able to find out the I enclosed, the current that passes through this Amperian surface, right? So this I enclosed will be equal to the J dot ds. Basically, J is the current density multiplied by the surface area will give me the total current that crosses this particular surface. Okay, so I can safely write my H dot dl. H dot dl, I will do this later on. H dot dl is equals to J dot delta S. Okay, or if I just integrate simply this thing, J ds double integration. Okay, surface integration. So if I take the surface, this is open surface integration. So now what I can do, I can simply apply the Stokes theorem. What is the Stokes theorem? If you remember, if I have a closed line integral, I can convert it into a surface integral, open surface integral. So this will get converted into del cross H dot ds. This is equals to J dot ds. So from this, right, I can safely say that my H cross del cross H is simply equals to J. So from here I find out the differential point format. This relationship that you should know, this is a good relationship. Okay, and this will be helpful actually in the examination as well, that my del cross H is equals to surface current density, volume current density J. Okay, this is the volume current density. So this you have to remember, or if you want to derive, you can derive as well. I have derived in front of you, so either way works. So this is the point form or differential form of Ampere's law. So this is also another Ampere's law only, but here we are relating with respect to volume current density. Okay, so this was the law. I just kept extra page just for the sake of it. I have to remove this page, so I'll remove this later on. So let's do a few questions. Okay, so this question came on GATE 2022 recently only. So here, if the magnetic field intensity H in a conducting region is given by the expression this, H is given, the magnitude of the current density in ampere per meter square at x equals to 1 to 1. So whenever they say ampere per meter square, that means it is the unit of what? It is the unit of current density. So remember here, actually this volume current density, the unit is not current per meter cube, it is current per meter square. Just like surface current density has a unit of current per meter. Okay, that thing you have to keep in mind. So here my volume current density has a unit of ampere per meter square. Whenever they say ampere per meter square, you quickly identify that they are talking about the volume current density. Okay, and they are talking about the differential format of the Ampere's law. So I know this relationship. What is the relationship? The relationship is del cross H is equals to J. Okay, so I'll just do that cross product. So what is del cross H? So basically here I can say that it is del x, it's in xyz coordinate, right? So things are very simple here. Del x, del y, del z, and okay, this should be here, right? This is ax, ay, az, and this is x square, y square, x square, y square, z square, x square, y square, x square, y square, z square. So this is equals to what? This is equals to this times this, so this becomes 2y x square z square, 2y x square z square minus 0. So this is only the ax cap component. Now let's do the ay cap component. Again, if I do this component, right, this will be 2x y square z square minus 0. So 2x y square z square ay cap plus the z cap component, right? Again, this is 2x y square minus 0. 2x y square minus 0. So this is z cap. Now what are the coordinates? Coordinates are, so this is my j, and where are they asking this j value? So this j value they are asking at x equals to 1 to 1. Okay, so this is at x equals to 1 to 1. So this will be simply 2 times 2 times 1 times 1 ax. Are they asking magnitude? They are asking magnitude. So I have to find the magnitude, and this will be minus 2 times 1. This is 2. Okay, times 4 times 1 ay plus 2 times 1 times 2 square az. So overall this becomes 4x minus 8 ay plus this is also 8 az. Now if I find out the magnitude, if I take the 4 common, this will be ax minus 2 ay plus 2 az. So if I take the magnitude, right, magnitude of j at point 1 comma 2 comma 1 will be equals to 4 times 3. So this will be 12 ampere per meter square. Okay, so it will be B. Option B will be correct. So like these type of simple questions come. Now next question is bit difficult. Okay, so I will recommend you to pause the video and try it by yourself. So here what are they telling? They're telling a long conducting cylinder. This also came in GATE 2022. So in the same year they asked from the same topic, exact same topic. Okay, they didn't even touch electrostat, they just touched this. That's like very unfortunate. So in GATE examination sometimes luck plays a very big role. During my exam, this was my year, and I don't remember whether I attempted this test because I skipped the electrostat, magnetostat part. So I wasn't able to solve this. If I would have been able to solve this, then maybe my rank would have been better. So let's see this. A long conducting cylinder having a radius b is placed along the z-axis. So the z-axis is this. Assume the z-axis to be this. This is x, this is y, this is z, and a long cylinder is placed here. This won't draw a circle that easily. Along the z-axis, correct? So what are they telling next? Having radius b, so it has a radius of b. The current density J is JA r cube Z. So current density, they have given me the expression for current density this time. It is JA r cube Z cap, right? It is in the Z cap direction. Okay, AZ cap. For the region R less than B. So if the radius is less than B, then the current density is this. Inside the cylinder, basically, they're telling me the current density. Okay, that's the basic thing they're talking about. Where R is the radial distance. Basically, R you can replace with rho as well. Okay, this is in the cylindrical coordinate system. So I will replace R with rho. It's my freedom, so I will do anything. So I will use the cylindrical coordinate system, so I will replace R with rho. The magnetic field intensity H for the region inside the conductor will be, what will be the magnetic field inside the conductor? So how do I actually find this out? They have given me the current density, so I have to use the Ampere's law again. So what I will do, I will again choose I will just cut this, take it to the next page. So what can I do is, I can choose a Amperian loop along the cylinder, right? Along the cylinder curve area, I can choose the Amperian loop. Now if I choose this Amperian loop, what will happen? Current density is always in the z cap direction. Okay, it's always in the single z cap direction. And if the current density is in the z cap direction, whatever the current may be, the magnetic field will always be a circular like thing, right? If current is in the z cap direction, I know the magnetic field direction will be always circular, surrounding this circle. So if I choose a Amperian loop like this, I will be able to find out the expression for magnetic field intensity. So my Amperian loop will simply be, now I will not choose it from B, I'll just choose, like I will assume it to be at some distance rho, okay, and my rho will vary from 0 to B, okay, that is from where my rho will vary. Rho is a variable, because like my answer will come in terms of rho. Here they have told R, because magnetic field intensity, they are defining R as the radial distance. For me, the radial distance is rho, simple cylindrical coordinate system. So I will choose, again I will choose, in most cases you have to choose either a square Amperian loop or a circular Amperian loop. So I will choose a circular Amperian loop. Now if a circular Amperian loop is chosen, right, so I will just copy and paste this. Now what is happening, what is the direction? It is in the plus AZ cap direction, right? Plus AZ cap direction, the current is in the plus AZ cap direction. So my what will be the direction of the loop? Direction of the loop will be something like this, correct? Along the fingers, okay. This is the direction of my DL cap vector basically, and magnetic field will also be in the same direction. Now what is the Ampere's law? What is the Ampere's law? I know Ampere's law is integration of H dot dl is equals to I enclosed. This time I'm simply using the magnetic field intensity, because they have asked me to find magnetic field intensity only. So what is this I enclosed? How do I find out I enclosed? I enclosed will be the amount of current passing through this cross section. Amount of current passing through this cross section, right? So it will be the amount of current passing through this cross section. So what will be it? So it will be simply, it will be simply J dot in J into delta S. Okay. So what is J? J is simply JAR cube, right? JA in our case rho cube. And what is the surface area here? It is simply pi r square, rho square. So we will get your answer as JA rho raised to power 5. And then what you will do? Then you can simply divide by this H dot dl. H will be constant here, right? So I can say this will be, each I can take outside, it will be into 2 pi r equals to JA, not r actually, 2 pi rho JA rho raised to power 5. So your H comes out to be JA rho raised to power 4 divided by 2 pi. And when you try to look at the options, you will see none of the options are matching. Then what is happening? So obviously you have done something wrong. So this, right, you should never do this. Should never do this. Where have you went wrong? Where have you went wrong? So basically here, right, simply just multiplying the area, it doesn't work like that, because your current density is actually a function of radius. It is a function of a variable. So what is the correct method to find out the total I enclosed? Total I enclosed will be what? Total I enclosed will simply be equal to integration of J dot ds. This is the correct thing, okay. And what will be the surface vector? ds will be in the positive AZ cap direction. So dx is simply AZ cap direction, right? AZ cap direction. So this will be here. So what will be my ds vector here? So what is my ds vector? How will I choose my ds vector? So I will just write my dl vector in cylindrical coordinate system. What was it? It was d rho a rho cap plus r d phi, right, or rho d phi a phi cap plus dz az cap. So your dz, like I know my surface, what is the surface vector? Surface vector is this, right? And the orientation is also given. It is in the positive az cap direction. So if it is in the positive az cap direction, I will just choose the other two variables. So it will be d rho, rho d rho, d phi and az cap. Correct? This is the orientation. So my surface integration will be simply this. So I am doing this fast because I hope you understand what does this surface integration mean, because I have spent my precious time just explaining all this in the lecture 0 prerequisites. That's why I spent the precious time there, so that you will be able to understand this thing in a second when I am applying this concept in actual questions. Okay, so that's why I spent so much time there. So it will be simply integration of j is how much? J is a function of rho, right? J is a function of rho. Where have they given? J is ja rho cube az cap. Ja rho cube az cap, and ds is rho d rho d phi. And how is my rho varying? So my assumption will be that my rho actually is from 0 to b, rho exists from 0 to b. I will assume that rho is going from 0 to r, some distance r from the center. Okay, some distance r from this positive z axis, right? So that is my assumption. So I will assume my rho will go from 0 to r, and phi I am rotating throughout this whole circle, right? Throughout this whole circle, because why am I keeping this rho from 0 to r and not from 0 to b? Because I need to find the magnetic field intensity as a function of radial distance as given in the options. Okay, so I will need to find out that. So that's why I am keeping a variable. That's why my rho is varying from 0 to r, and this is varying from phi equals to 0, not enough space, phi equals to 0 to 2 pi. Okay, so this will be equals to what? So I can observe that this 2 pi will be outside because this is not a function of phi itself, and here also there is a az cap, right? I forgot there is a az cap, and these two will be dot product. 2 pi I can multiply outside, and this will be ja will be outside. This will become rho raised to power 4 divided by 4 from 0 to r. Not 4, sorry. This is already getting multiplied. Rho raised to power 4. This will become rho raised to power 5 by 5 from 0 to r. Okay. So overall this becomes 2 pi ja r raised to power 5 divided by 5. Okay, and what about the left hand side? This was the I enclosed. What about the left hand side? So I know integration of h dot dl. Again, h magnetic field will be a constant, and the angle between that will be simply same, right? So angle will be 0. So this again I can convert this into h dl cos of 0, and dl going from 0 to 2 pi small r, the distance from center. Correct? This will be equals to h into 2 pi r. Okay, and this is equals to what? This is equals to this thing, right? So I can safely equate these two things, ja r raised to power 5 divided by 5. So here what is happening, 1 r will get cancelled, 2 pi will get cancelled. So overall my my electric field intensity will be equals to what? My electric field intensity will simply be equals to 2 will be ja r raised to power 4 divided by 5. Okay, and what is the direction? Direction they have also not told us. So it is in the arrow gap direction, right? So I can comment here from here itself. The direction of the magnetic field will be arrow gap direction. Not arrow, sorry, a phi cap direction. Arrow is radially outward. Direction of the magnetic field will be along this cylinder. Okay, along the curved surface area of the cylinder. So it is Ja r raised to power 4 divided by 5. Ja r raised to power 4 divided by 5. Option C is the correct option. Okay, so yeah, this is correct only. So I hope you got understood the point how we solve all these things, right? I have understood how we solve these things. I hope all these things are clear, because this point is actually important, because this question was very good. You can make a very silly mistakes here, and all these things have been taught very well in the lecture 0, like starting of the this whole subject itself. Okay, so I hope you understood the thing. Okay, so now let's move on to derivation of few other magnetic field expressions. So what will be the magnetic field on a solenoid? Okay, in a solenoid, I hope you know, solenoid is simply a wire current carrying coil with a multiple turns, right? If I put multiple turns, it just behaves like a bar magnet, as explained in the previous lecture. If I put multiple turns in a solenoid, it will just behave as a bar magnet. And what will be the current at the center of this solenoid? Okay, so this thing, actually what I can do is I can totally replace this thing with these type of circuit. Now what is this circuit? What is this cylinder? So this wire, if I assume the current to be going inwards, it will come outside from here, right? It is going inwards, then coming outside. So this is telling me that, okay, it is the opposite, other way around. So it is telling me current is flowing like this. Current is coming outwards, then inwards. So this is telling me the top half, all the current are coming towards me, and the bottom half, all the current are going in. Okay, so that is the visual representation of this wire, like to give us some information. So actually I want to find out the magnetic field inside a solenoid at the center. So can you tell me, can you guess what kind of Amperian loop I should choose here? What kind of Amperian loop I should choose to identify the magnetic field lines here, right? Magnetic field lines will be something like this. Why it will be something like this? Because just simply curl your fingers, right? If you just simply curl your fingers along the current loop, okay, you will see it is just your thumb is pointing towards the magnetic field, so it is just a straight line. So magnetic field will be straight here almost. It is not like a circle. It is not like a circle. So that is the hint. Tell me what type of Amperian loop I should choose. So of course I should choose a rectangular Amperian loop here. Okay, I will choose a rectangular Amperian loop. Why shall I choose a rectangular Amperian loop? The reason is simple. Why? Because this time magnetic field is linear, not circular. Magnetic field is linear at center. Okay, so what kind of Amperian loop? I will just choose a square Amperian loop. If I just choose a square Amperian loop here, not square, sorry, rectangular Amperian loop here, and mark the points A. Let me choose a deep color. Okay. A, B, C, D. So these are the 4 points actually here. These are the 4 points here. So what is the I enclosed here? So let me assume this length to be, like I can assume a square Amperian loop as well. Okay, doesn't matter, because like why it will not matter, I will explain. This length to be L. Okay, and this is also L. Okay, and this length actually doesn't matter. Why it doesn't matter? Here if I observe, the magnetic field is in this direction, and what is the direction of the Amperian loop? I will assume it according to the direction of the magnetic field, right? Magnetic field is something like this, or according to the current enclosed, whatever one you choose. So magnetic field is in this direction, so I will assume the Amperian loop to be in the same orientation. Okay, so the direction of the Amperian loop will be same orientation. Okay, fine. Okay, so now can you tell me what will be the magnetic field here, right? What will, like, there will be 4 sections here, right? So if I apply the Ampere's law, integration of B dot dl equals to mu I enclosed. So it will be integration of B is this, okay, for section 1 plus this is the I will just write here BAB, not closed loop anymore, this will become open. Integration of B dot dl for BC plus integration of B dot dl for CD plus integration of B dot dl of dA. Okay, so what will be the magnetic fields due to the all 4 components? Here if I observe that my assumption is at the top, right? At the top actually the magnetic field is 0 simply. Why it is 0? Because, like, if you observe a solenoid, you will observe that this magnetic field just near the wire at the top is simply 0. It just behaves like a bar magnet. Okay, so the magnetic field at the top will be 0. So this CD section, it will be simply equals to 0. What about the DA section and the BC section? So in D and BC the magnetic field is present, but it is actually this dl vector is in this direction and magnetic field is in this direction, it is 90 degree. So actually I chose you, right? I told you to what are the tips to choose the Amperian loop. So this was one of the tips. The magnetic field should either be 90 or 0 degrees. So here I'm observing that magnetic field is always 90 degrees. So as here magnetic field is always 90 degrees, this will also be 0. I will write here theta equals to 90. Here it is also 0, theta equals to 90, and here it is simply 0 as magnetic field itself is 0. Only the magnetic field due to the section 1 is there, right? And this is, like, we'll assume this is some constant, and the what is the direction? Direction is same along the direction of this L vector. Okay, along the direction of this L vector. So it will be simply equals to B times dl, and cos 0 is there. Now what is the I enclosed? What is the I enclosed? Now this is coming towards me, and what does the Amperian loop tell me? Amperian loop also tells me the positive direction is coming towards me, so this will be positive. Now what is the, like, if I just choose Amperian loop, like this whole Amperian loop, right? If I just choose this as a whole Amperian loop, what is the total current that comes towards me? So here I have given you parameters like N and I. N is the number of turns per unit length. Okay, N is the number of turns per unit length, and I is the current in the solenoid. Okay, so if N is the number of turns per unit length, so here how many turns do I have? L times small n. As if I multiply L with small n, I will get number of turns in this particular length. Okay, and that many turns I have. Total current is I, like each turn, right, has I current. So overall N times L will have NL I current, right? So this will be N times L to get the overall number of turns in L length into I to get, like, each turn has I current. Okay, and this also is, this DL will also go from 0 to simply L, correct? For the AB section I'm talking about. So this becomes what? This becomes B equals to mu is also there, right? Just don't forget the mu. B becomes mu Ni, and this is the simple expression, right? mu1i. That's a simple like derivation of solenoid. You can remember this formula. This is good to remember. Okay, or you can like derive this, but derivation is bit weird, so I will recommend you to remember this particular formula, that at the center of the solenoid, right, the magnetic field will be mu1i. Now you are telling me, sir, at the center it is mu1i, so at the ends will it be different? And I will say yes, at the ends it will be different. At the ends it will just be half. Why it will be half? Because if you just see here, it is getting divided into this section and this section, right? So into two sections it is getting divided. If you observe the magnetic field as well, one end is going up, other end is going down. So obviously if I assume it's symmetry, so magnetic field at the ends, so B at the ends, B at the ends, right, will simply be mu ni by 2. Okay, so that will be the case here. So yeah, like I have just written the formulas. These formulas you can remember. Okay, I hope you understand why at the ends it is getting half, because half of the fields will go up, half of the fields will go down. That's the simple reason. That's it. Okay, so let's do a few questions on this. Okay, I hope you understand this point. What do I mean by n? N is basically number of turns per unit length. So let's say n is equals to 2 per meter. Okay, so if I have this length is 1 meter, so how many number of turns will I have? I have to multiply 2 into 1. If I multiply 2 into 1, I will have 2 turns. So what does this n represent? If it is equal to 2 per meter, that means I have 2 turns per meter. So in a meter I will have 2 turns. In 2 meters I will have 4 turns. So I just have to simply do the linear multiplication, and that is what I did, right? This gives me the number of turns. This gives me the number of turns in L length. Okay, so that is the case basically here. So here, if I want to solve this thing, a solenoid with 1000 turns per meter has a core of relative permeability 500. So my first time some relative permeability comes 500, and it has 1000 turns per meter. So n is equals to 1000 per meter. The solenoid's insulated winding carry a current of 5 amperes. So I is equals to 5 amperes. Calculate the magnetic flux density generated by the solenoid. Whenever they talk about this magnetic flux density, you will assume magnetic flux they are talking about at the center. So this will be B will be equals to what? I have just derived the formula. B is equals to mu ni. First time I am giving you a simple question, just putting the values, because the concept of turns per length may not get totally into your head, so I just wanted to clear it out. So it is B equals to mu ni. So mu is how much? Mu r mu naught, right? So mu r is 500 into mu naught is 4 pi into 10 raised to power minus 7 into turns 1000, ni and I is 5. So this becomes, here I have 2 zeros, 3 zeros, 5 zeros, so this becomes 10 raised to power minus 2. And this is 5 into 5, 4. Another 2 zeros comes, so this also gets cancelled. So only I am left with pi. So this will be pi Tesla. This will be the magnetic field. So pi Tesla is simply 3.14 Tesla. So this will be the solution for this particular question. Pretty simple question will come from solenoid if it comes. The next concept is toroid. Same as solenoid, what we did with solenoid is, actually I don't like, why are we making a solenoid? To get a permanent magnet like this and to control the magnetic field. This permanent magnet, I am not able to control the field strength, but with the help of a solenoid, if I control the current, the magnetic field strength will be controlled. So I want a permanent magnet like field with controllability. That's why we made solenoid. But in solenoid there was one deficiency. What was the deficiency? At the ends the magnetic field was getting reduced. I don't want that. So what I did, I just connected the ends. So toroid, what I did was simply I connected the end. So here, that is what I have written over here, and the spelling is wrong of solenoid, so it will be solenoid. Okay, so I just bent it to improve magnetic field density. Okay, so if I connect it, now can we derive the expression for a magnetic field? So how will the magnetic field be? So current will flow something like this, right? Current, like if I assume a direction, if I just assume a direction here, current will be okay, this color is not that good, I'll choose this color. Current will be just like this, right? It will come here and go in. Okay, so from somewhere here, this for some reason has been, like, what will happen is, this was supposed to come here. I will just draw this. Two wires supposed to be here. Okay, one wire was at the inside. I will just do this. One wire will be something like this, other wire will be coming from somewhere here. Okay, so what will happen? Current, this flows out, this flows out. Okay, no, not this. Current will simply be coming out here and coming in. Okay, so it will just flow in like this and go out. So what is happening, if I observe at the top surface, right, I can observe it is coming towards me, current is coming, pointing towards me. At the bottom of this, current is going out. Okay, current is going into the screen. Here bottom, current is going into the screen. At the top, current is coming towards me. And where will the magnetic field be? So if I just curl my fingers along the direction of the current, I can observe that my magnetic field will be something like this. Correct? So magnetic field will be along this periphery at the center of this like ring shaped thing. And what will the direction of the magnetic field will be? Again in the clockwise. Why? Just rotate, right? Rotate your fingers along the direction of the current. You can observe the thumb is just in the clockwise direction. It's in the clockwise direction, right? So it will be in the clockwise direction. So here what I can say is the magnetic field will be circular in shape. So again, if the magnetic field itself is circular in shape, what kind of Amperian loop will you choose? You will choose a circular Amperian loop. So we'll choose a circular Amperian loop. So here we'll choose a circular Amperian loop. So the Amperian loop will be somewhere totally here, right? Because it is somewhere between. So this is the top surface and this is the bottom surface. That's it, right? Just I have demonstrated this thing. This is the top surface where current is, like here I assume the opposite. Basically current is here, current is going in, so current is going in just the opposite direction, and here current is coming out. Okay, that's it. So current going in and out, going in and out, going in and out, just all the wires are wrapped. So this is not actually empty. This is the particular ring, right? This insulated ring. Okay, this is not empty actually. Okay, just to show you a visual representation. So here magnetic field will be somewhere in between, right, in this ring. So magnetic field will be somewhere here. Okay, so again I will choose a circular Amperian loop. So I will choose a circular Amperian loop. So this will be the, okay, sorry, this will be the Amperian loop basically. Okay, and what will be the direction of the Amperian loop? Again, please put your fingers along the direction of the current. So at the top of this, it is going inside, and at the bottom it is coming towards me, right? So it is on the left hand side. It is like left hand side. It is like a anti-clockwise direction. So the direction of the Amperian loop will be in the orientation. The Amperian loop will be in the anti-clockwise direction along the direction of the magnetic field, right? Okay, so that is the orientation. Now what is the I enclosed by this surface? What is the I enclosed? Here each particular turn, right, is carrying a current of I, and how many turns I have? N total number of turns. So again I will use the same formula, same Ghisa-Veta formula. Okay, that is this time I will not use H, I will use B. B dot dl integration, closed line integration is equals to mu I enclosed, right? So what is I enclosed? It is mu into I enclosed is how much? Total number of turns I have n. So this has n turns and total I is coming out of the screen, which is in the positive direction along the Amperian loop. Amperian loop is also telling coming out is positive. So it will be Ni, and this will be equals to what? This will be B into dot dl, right? B dot dl. So B dot dl will be simply B into 2 pi. What is the length of this? 2 pi r, right? And r, I will assume r is this mean radius. Okay, capital R. This is the mean radius between these two smaller, because this section itself also has a radius, but I will assume it to be mean radius. So B will come out to be mu Ni by 2 pi r. This r is a constant thing, right? This is a constant. Okay, so it only depends on the current. The magnetic field only depends on the current. It actually doesn't depend on the total what do you say, distance, right? It doesn't depend on the distance, it only depends on the current. Now can we further break this down? Can you tell me what is the number of turns per unit length? What is the number of turns per unit length? How to find out n? N is total number of turns divided by length. So total number of turns is n. That is simple. What is the length? Length is simply 2 pi r, because in this whole 2 pi r, in this whole 2 pi capital R length, I have n number of turns. So this will be 2 pi r. This is actually not small n, sorry. This is capital N, right? Missed a point here. So 2 pi r. Now obviously, am I observing this somewhere? Yes, here. Correct. So I can again replace this with mu by Ni. So this becomes the same formula as the solenoid. Okay, this becomes the same formula as solenoid. So I have just written it here only, that your magnetic field for a toroid will be simply mu n capital Ni by 2 pi r, or it will be mu small ni, same formula as solenoid. That's it. What is the advantage? Advantage is we get constant. There previously, here actually I should have drawn the graph, like actual plot of a solenoid practically is something like this. If I just move in the some radial distance from this, right? So let's say further r, what will happen is along the linear distance L, I will say this is the magnitude of B. So it will be something like this. Okay, I should change the color probably. So although this is not perfect, I just choose this better. So at the ends, my magnetic field becomes mu Ni by 2, and at the center my magnetic field is mu Ni. Okay, and I don't want this actually. I want a constant magnetic field, right, throughout. Okay, to do that we do this, right? We basically connect the ends, so it becomes a toroid, and throughout I get a constant magnetic field, not along phi. Okay, this is along phi only because I'm moving along phi. Okay, so if I'm moving along phi, I'm getting a constant magnetic field profile, which is mu Ni. Okay, so that is what I want. So that was the reason. And few terms you should know basically, that r is the mean radius. So if it gets asked in the question, how do you compute the mean radius? Simply you do the r outside plus r inside divided by 2. R outside is what? R outside will be the distance from the center to the outside surface. Okay, basically this surface, right? This surface. And r inside will be distance this, and the mean is simply the average. Okay, arithmetic mean of these two in between. And n is the number of turns per unit length, which is given as n by 2 pi r, and you can compute the other thing. And what is smaller? Smaller is the radius of the circular core, because the core is also a circular, it's just like a ring, right? So it is also circular, and the smaller is the radius of the circular core. Okay, so I hope you get the point. Now let's do a small question on this. Okay, we have a toroid made of non-metallic material, has an average radius of 0.1 meter. So its average radius or the mean radius capital R is 0.1 meter and 500 turns. Total turns is 500. It is not turns per unit length, it is total turns. If it carries a current of 0.5 amperes, I is 0.5. What is the magnetic field intensity along its circular axis in Tesla? So simple question, right? Simple formula based question. So we didn't have, like, I didn't have many questions on toroid. One question is there in the self inductance chapter, so that we will solve. So this is very simple, right? So B will be what? B will be simply equals to mu n I divided by 2 pi r, right? So this is, they haven't told anything, so I will assume it to be in the vacuum. So it will be 4 pi into 10 raised to power minus 7, n is 500 into 1 by 2, I is 0.5, and this is 2 pi into r is 0.1. So this comes out to be 2 pi becomes 2, 2 gets cancelled, this is 505,000. So this is 5 into 10 raised to power minus 4. Okay, so yeah, that's basically it. This is 5 to 10 raised to power 4 Tesla. In Tesla, this is the answer, right? If they could have asked in nano Tesla or something, so but in Tesla, this is the answer. Okay, so there is one more thing that is basically left still. So I will just remove this page quickly. One more thing is left. Last thing is the magnetic field due to a infinite sheet of current. What will be the magnetic field due to infinite sheet of current? So if I have a sheet, okay, which is infinite, just like infinite charge, but this is not charge, this is current is flowing actually. Okay, so how will I find out the magnetic field at a distance d from the infinite sheet? So again, what thing comes to your mind? Okay, what kind of Amperian loop comes to your mind? If I observe, if I just, this is the like top view of this particular thing, and this is the front view, right? If I see front view, all the current is coming towards me. All the current is coming towards me. That's why it is like a dot thing. Okay, all the current is coming towards me. So what kind of Amperian loop you might think? So due to all of this current, right? If I just place this current and curl my fingers, I am observing the magnetic field will be leftwards. Correct? Magnetic field will be something leftwards. And I'm observing that due to all this current, right, it will be something like a straight line. It will not be a circular anymore, because it was supposed to be circular if I had a single current carrying wire, but now it is a sheet. So if it is sheet, it will just be like a straight magnetic field, right? Magnetic field will be in this direction. So again, if magnetic field is in this direction, I can say that I have to choose an Amperian loop. Okay, and another interesting fact, if you want to find out the magnetic field due to this individual components, so I have written that here. So if I just want to find out the magnetic field due to this individual component, I will again place my thumb on the direction of the current, and I am observing this is on the left hand side. Okay, somewhere on the left hand side. Like what I will do, this is the direction of the current, and then I will do the dl cross r. So if I do dl cross r, this will be somewhere in this direction, and due to this, the magnetic field will be somewhere in this direction, and due to this one, the magnetic field will be somewhere in this direction. So what will happen? Ultimately, the vertical components will get cancelled and the horizontal component will be left. This is the symmetry basically. That's why we are able to use the Ampere's law. So that is written: adjusted line current cancel the vertical components of each, leaving only the horizontal component. So only the horizontal component will be left here, and in what direction? In the left hand side. Again, I will say, as magnetic field is linear, we choose, just let me check if everything is recording or not. Yeah, everything is recording fine. Everything is recording. I'll just quickly check few things. Yeah, everything is fine recording. So here what I can say is, we choose rectangular Amperian loop. So if I choose a rectangular Amperian loop, how will I choose? So basically this is what I was talking, right? This, due to this component, the magnetic field will be somewhere here, and due to this the magnetic field will be somewhere here, and both of these will cancel the vertical components, only the horizontal component will be left. Okay, so here if this is a distance x, right, from this particular center, and I want to compute the magnetic field here, I can choose a Amperian loop. Okay, I'll just copy this thing, just copy this thing, and I will just choose an Amperian loop. Now as it is symmetrical, what I can say, if this distance is d and this distance is also d, right, so obviously the magnetic field here will be along this direction, and magnetic field here also will be same magnitude but in the opposite direction. Okay, this is symmetry. So I can choose a rectangular Amperian loop as mentioned, so I will choose that exactly. So I will choose something like this. Okay, although it is seeming like it is very big, but it is not actually that big, it is very small. Okay, so again, as the magnetic field is in this direction and in this direction, so what I can safely say is that I will just do one thing. Actually I needed to make it more smaller. How do I make it more and more smaller? That is the problem actually. Actually I wanted to show that it will lie somewhere around here, right? So I'll just do this rough drawing. Okay, that the magnetic field, let's assume this has d distance, and this has d distance, and this is the magnetic field direction here, B, and this is also the loop direction, loop orientation. The loop orientation will be in the same direction as the magnetic field. Okay, and this is the magnetic field direction here. Okay, like not magnetic field actually, this is a loop direction. And what is the magnetic field? Magnetic field will be like this. Magnetic field lines will be parallel straight lines, right? And here it will be on the right hand side, correct? So if I just name this loop again A, B, C, D, what do I observe? The magnetic field here, simply closed magnetic field B dot dl along A, B, C, D, A will simply be equals to mu into I enclosed, correct? And what is the I enclosed here? What is the I enclosed? That we have to identify. We'll identify that later on. But first, let's try to do the B dot dl, right? So it will be equals to B dot dl AB plus B dot dl BC plus B dot dl CD plus B dot dl DA. Okay, so one thing I observed, that due to this BC and DA, again the same thing is happening. They are again what? BC and DA, they are again perpendicular, correct? Simply perpendicular. All the magnetic field lines are perpendicular. So if they are perpendicular, so this will be theta will be 90, and this will also make theta as 90. So obviously they will be simply 0. Okay. So these are 0. What about this? So here I will assume this has B net, magnetic field is B net, and theta is simply 0 degrees. This also, here also theta is 0. Surprisingly, here also theta is 0, right? My magnetic field and the direction of the loop is in the same direction. So here also theta, not this, sorry, not this, this one. Theta is 0 and this is the B net. Okay. So that is the case here. So what will happen here? So what I can say is, what I will get on the left hand side, it will be simply B net to B net integration of dl, right? That's the case, right? It will be simply 2 B net integration of dl. That's it. Now what about the right hand side? What will happen to the right hand side? So again, on the right hand side, I haven't told you about the variable, that is, this has a surface current density of K. Now don't confuse this with the area. This is actually meaning that how much current is flowing per unit length. Okay, per unit length. So if K ampere per meter current is flowing per unit length, and if I am using this much amount of section, so how much current will actually flow in this particular length? It will be K times L, right? In this particular length, it will be K times L, because its surface current density is K. So it will be K times L, and surprisingly, the biggest surprise is it is coming towards me. It is in the same direction as the positive direction of the Amperian loop. So it will be plus, it will not be minus. And obviously there is a mu here, right? Now this dl is also what? I'm integrating from 0 to L. I'm going from 0 to L, correct? So obviously my B net, magnitude of B net comes out to be, surprise, magnitude of K vector divided by 2. So this is a very, very important expression that you should know, and you can remember this as well. This is a good thing to remember. Okay, just what analogy I can give you? Just remember, in electric fields, if I had a infinite sheet of charge, the electric field due to infinite sheet of charge was rho s upon 2 epsilon. If you are able to recall that thing, the same thing is happening here. Okay, just this epsilon is not in the bottom, it's in the top 2. Okay, same thing. So I hope you understand this point. Okay, now how do you identify the direction of the magnetic field? How do you identify the direction? What you can do, you can simply take the K cross R vector, right? What you can do the K cross R vector. That will give you the direction. So what is the R vector? R vector is this, right, pointing outwards from this plane. That will give you the direction. Okay, so yeah, that you can find out, you can understand the direction will be here left. Okay, just simply do the cross product and that will give you the direction. So this AB cap will give you the direction, magnitude of K cross R divided by, not magnitude, sorry, K cross R vector divided by magnitude of K cross R. Okay, that will simply give you the direction that is perpendicular to both of this, right? And it will be ideal cross R, right? So okay, I is there, ID, okay, DL is here, and yeah, ideal cross R, yeah, it is K cross R only. So this will give you the direction of AB. So your B net, I can properly write it in a better way. B net will be equals to mu magnitude of K in the A B cap direction, and AB cap will be what? Simply the perpendicular to both K vector and R vector. K is simply the current element and R is the perpendicular distance. Okay, I hope you get the point. R is the perpendicular distance. So according to this, I will give this as homework. Can you solve these questions? And in the next lecture I will solve these two questions. It's very very easy. Just you have to identify the magnetic field at point P due to the two infinite sheets of currents. Okay, not charge, currents. So that's basically it about this lecture, and in the next lecture we'll do this homework question and we'll do boundary conditions on magnetic fields. So that will be also a very interesting lecture, so please do watch it. I will derive everything, okay, because I have seen many students get confused in the magnetic field boundary conditions because things are not mentioned clearly. So we'll derive everything with the help of Ampere's law and with simply the magnetic field characteristics. Okay, so that's basically it for today's lecture. I hope you enjoyed this lecture, and I will see you in the next lecture. Until then, happy learning.